So what I want to do today is go over how to synthesize transfer functions in the the DF2 methodology. And the reason why we like DF2 instead of DF1 is that the potential to save OPAMPS, because DF2 shares integrators and DF1 does not. So I'm just going to briefly go over a higher order polynomial, and then we'll start working on simpler ones. But in order to see the full process, we kind of have to use something more complex. So we have two polynomials, one in the denominator and one in the numerator. And for the numerator, we start with b0 times s cubed plus b1 times s squared plus b2 times s plus b3. Then in the denominator, we have s cubed, and it's important that to get your polynomials to where the constant before this is 1. So there is no b0. There's no a0. So then we have a1 times s squared, a2 plus s, and then just a constant. So this is like standard polynomial format. And we'll find that we will not always have every order of s in the denominator and the numerator. So we need to convert this to integrators, right? Ultimately, all these circuits will be synthesized using inverting integrators. While there are non-inverting integrators, for this methodology, it's actually just a lot easier just to use the inverting one. So really, this is just 1 over RCS, and we can set RC equal to 1, minus sign, so that really we can get minus 1 over S. And we'll worry about that minus sign later. So to convert this into integrators, we actually divide through the numerator and the denominator by the highest order of S in the denominator. So in this case, we have S cubed. So now we'll divide through by S cubed and S cubed. So if I divide this by S cubed, I just get B naught. B1 times S divided by S cubed, I get B1 divided by S, B2 divided by S cubed, squared, and B3 divided by S cubed. And so here's our integrators. So single integration, double, and triple. Then when we do the same thing for the denominator, we just get 1 plus A1 divided by S plus A2 divided by S cubed plus A3, A2 S squared, A3 S cubed. So this is our standard format to help us remember how to synthesize this. And so this will be in the cheat sheet. But you can see here's B1, here's B2, here's B3, minus A1, minus A2, and minus A3. Now here's the thing, it doesn't show it like this, but in fact, the fact that these are all plus signs indicates that that's negative feedback, and so we need a minus constant. I'm not going to go over that why is that right now, but we'll just continue on. So now that we have it all like this, we can just figure out how many integrators do we need. Well, if I have s cubed, the easiest way to get s cubed is to pass it through 1 over s times 1 over s times 1 over s. So we're going to need 3 integrators. All right. Now the summers, that could be a little trickier to do. And what the book does is to make this picture look very symmetric, is it only adds 2 signals at a time. But summers can certainly add more than 2 at a time. So when we're adding B0, B1, and B2, right? 1, 2, 3, 4 things to add, right? And in this example, what's missing is B3. Because in the book, they're doing a specific example where I'm trying to keep it more generic. So there's 1, 2, 3, 4 constants that are all being added. So you definitely need a summer, but you don't need 1, 2, 3 summers. You can use 1 summer, which means 1 op amp. So I'm just going to say 1 summer for Bs, okay, which is 1 op amp. 3 integrators, 1, 2, 3. That means 3 op amps. I just wanted to make sure that I was recording. Sorry about that. Now, over here where we have the input, and we'll always need a summer here because there will always be some negative feedback. But so we have 1 summer, this signal's being summed, this signal's being summed, and so is this signal, but we can do all of that with 1 summer. So 1 summer for A's and input. All right. So 1 op amp. So if we sum the op amps, 1, 2, 3, 4, 5. 5 op amps. So right now, this example, it was somewhat random. We just added every possible term there was. But let's try to compare this to a low-pass filter. And I'm just going to keep it generic. So we'll make it first order, right? Just to show the difference. So the highest order of S is 1. So we're just going to multiply through by 1 over S divided by 1 over S. We will get omega naught over S times 1 plus A1. Excuse me, I jumped ahead of myself. Omega naught over S. Now the A's are pretty easy because it's 1 plus, this is the first order one because it's just 1 over S, so that becomes A1 over S. Now, in this case, at first there was no S term, but when we divide through to turn it into integrators, now that constant does have an S associated with it. All right. And so what that would look like is the signal would come in, it would go through an integrator, and then come out. So in fact, because it goes through one integrator, it'll be a little more easy for us to actually call that B1. All right, because it's going through one integrator. If when we multiply through by 1 over S and 1 over S, there was no integrator term over here, oh, well, then we would call it B naught. And like I said before, we don't always have every constant, so we just have to be careful. Alrighty, so we have, let's move into our circuit. We have our B's, and we have our A's. And we've identified, though, there's one integrator that we're sharing, so I can draw that integrator first. All right, now, so if you recall from up here, right, the signal came in, it's going through one integrator, and then we have to multiply it by B1, all right? And so we're not adding anything, but we do need to somehow change that value. Now, there's more than one way to go about it, but not only that, this is inverting. So what I have to do is add an op-amp here, and now I can call that out. And I can call this resistor B1 because I'm going to use it to calculate the gain here, B1. So RF will be fixed. I'll try to keep the RFs all the same. And I can have R1 and C1 here. Sometimes you can't always do this, but if I have R1 times C1 equal to 1, right, then, and I keep RF fixed, I can set B1 to make this omega naught term by setting that resistor, and that's the out. All right. Now, of course, there was a summer that came before it. I'm just drawing it a little bigger. All right. And what I do first is I draw the feedback resistance here, and I'll call it RF. And yeah, to try to minimize the number of separate parts, I'll have this RF equal to that RF. And then over here, to use that relationship, I'll keep that RF here. Now, how does the signal come in? Well, we have to we can't connect it directly to the node, otherwise it would just be the input, and I can name that resistor the in, because that'll be what I use to set the gain. So we've done this, right? And now we need to do the feedback part, and I'm just going to come back up here, right? We have the signal, it goes through a summer, non-inverting summer, through an inverting, unfortunately, integrator, times, in essence, what we did is minus B1, and then that just comes right out because there's nothing else to sum. So yeah, this was minus, this transfer function was minus 1 over S, and then this will be minus RF B1 times minus 1 over S, which will ultimately give us our omega naught over S term. Now, this is negative feedback, so this constant is supposed to be minus, right? Well, it's already inverted, okay? Even though, like I said, there's a plus sign here, that plus sign comes about when you mathematically take this circuit and solve for it. It turns out that it's a plus. So it's coming out, okay? It's already negative, so we don't want to invert it again. So in this particular example, all right, and then there's one more thing. So for this particular homework, you don't need to calculate the resistances, right? But you do need a resistance here, and the gain of the negatives needs to equal the gain of the positives, and so you can just set that eventually with like R dummy in this particular example. How to actually do that is in a case study for the bandpass filter, and I believe it's a 5th order low pass filter. I have a video and notes on how I calculate all of those things. But for this homework, we're just trying to estimate, for one, we're trying to estimate the number of op-amps. So let's go back to our original thing. So how many integrators do we need? Well, because it was first order, right? First order, 1 integrator, 1 op-amp. Now, one summer for the Bs. Well, we weren't summing anything else, but because this was coming out inverting, we had to add an op-amp to set the gain right. Now, for advanced circuit designers, I could switch the input to inverting and get it to come out the other way, and I could probably get rid of that op-amp, but let's just stick to this structure for right now. So even though I'm not summing anything, I still need one gain, or it's really a summer with one signal, right? Then I have another summer for one summer input and feedback. So here, three op amps, to do this low pass filter that you can do with this. Now, you might ask yourself, why would I ever do this when this is so much simpler and uses less parts, right? Less parts means less things in the landfill, less manufacturing, less testing costs, it's better for society. Well, we only did this to learn it. And yeah, sometimes there's more than one way to do things, and then you have to evaluate which way is the best way to go about it. All right, so you have to know more than one way to have choices. Now let's do another first order circuit. Right? The high pass. And we already know that this is most likely the most efficient way to go about it. Well, let's continue with our example. So it's a first order circuit. So we just multiply through by 1 over S and 1 over S. And now we get S times 1 over S is 1 over nothing, or 1 over 1. All right. Excuse me. And this turns out to be the same. 1 plus omega naught over S, right? Which, so I have 1 times 1 divided by 1 plus A1S. So notice this is exactly the same as what we had over here. And so in fact, this summer, everything will be the same for the negative feedback, the A's. The only thing that'll change is where we take the output and what we have to do with it. So let's put it into context. So this is just a constant with no integrator term to it. So if we go back here, right, we had S divided by the order of the circuit, which was S, so it canceled out. That would be as if we had B naught times S3 divided by 1 over S cubed. So really, there's no integrator. The signal comes in through the summer and then gets modified, and it comes right out. So that's just B naught divided by no integrator, right? 1 plus A1 over S. All right, so let's just redraw everything. Again, this is kind of my basic summer structure, and I'm going to do that. So really, I can set all of these resistances properly. So in fact, this right here is actually node B0, Now, sure, it goes through the integrator. Right? Now I have -1 over S. And there is another way to draw these. You can just bring it back like this. All right, it's equivalent. But here's the thing, these values would all be the same. That R1 would create that omega naught constant, or the RA1, right? And this R dummy, right? But here's the thing, this, in fact, is where we take the output. And because B naught equaled 1, and I don't necessarily need to put an op amp there. Now, sure, whenever you take an output and you don't necessarily know where it's going, yep, you might want an op amp for just to buffer the signal. All right. So again, this is like the summer for our Bs. There's only one, so it's just, and the gain doesn't need to be set, so it's a buffer, right? Here's our op amp for our inverter. Here's our original summer. We use 3 op amps. Now for the homework, you would just have to draw this picture. You don't have to calculate all these values. Now, so far we've just done first order, low, and high pass. There's other filters known as bandpass, but in fact, the minimum order to get a bandpass filter is 2. And this is the generic format. Some of these values, all right, we would, we're going to talk about later, all right? But we can see that it's a second order circuit, so we need to divide through by 1 over S squared divided by 1 over S squared. So that will give us omega naught divided by S, 1 over 1 divided by S squared divided by 1 over S squared is 1 plus 2 omega naught S plus omega naught squared S squared. All right, well, this term is associated with one integrator. So in fact, that means it's going to be B1 divided by S, right? This term is with one integrator, so that's going to be A1 divided by S. This term is with double integration, so that's going to be A2 divided by S squared. Now, just looking at it, right, the order is 2, that means we need 2 integrators, 2 op amps, right? We need 1 summer for input plus A's and 1 summer slash gain for the B's. So that's 2, 3, 4 op amps. So when you're, now we have multiple summers, we haven't done that before. Multiple integrators. So I'm going to draw them first. And I like to draw them in this pattern because it makes it a lot easier for me to not to forget to do the right thing. All right. Even if you're doing it in LT Spice, drawing it like this makes it so that you'll, won't make a mistake as easily, right? And you can't always do it this way, but I can start off by doing R1 and C1 and trying to make them all the same, right? So there's my 2 integrators, right? Here's my summer. I'm just going to put in 1 dummy resistor, if you will, right there. That is RF. And I'll put that RF. And there's my N. Okay. Now this is that first summer. It goes through an inverting integrator, right? And we want it to be negative, right? Because it's negative feedback. So in fact, all we have to do is keep it negative. So if it's already coming out negative, we keep it on the positive side because it doesn't change the sign. But for now we have an A2, which we didn't have before. We still want that to be negative, but notice this would be minus 1 over S, minus 1 over S for plus 1 over S squared. So in fact, we have to invert it. And I'm going to call that RA2. All right. Now, where do we take the output? Well, we had B1 over S, so let's just go back to our thing here, right? So it goes through 1 integrator, and then we have B1. All right. So we come back here. All right, we went through 1 integrator, but remember, that's minus 1 over S. I have to invert it at the very least. I can draw this. There's my inverting amplifier. And I can call this RB1 RF and label that out. So I had 1 op amp for each integrator. Yep. I had 1 op amp for the summer for the A's. Okay. And the input. And then, yeah, I couldn't get away from this other op amp. I needed an op amp to invert it and set the gain. So that prediction of just counting things up, yeah, it worked pretty well. 4 op amps. So I have more complicated examples. It's called the bandpass case study. and the 5th order Butterworth low pass filter. So if you want to see even more detail and higher order level of circuits, you can watch those videos.